Hello, on this edition of a lab demo, lab code review, we are going to be discussing the lab 3 code and how successfully we wrote, or my work was writing two communication protocols which are successful. The first one is I2C, and to discuss this, well, just generally, with our keyboard input, all our input was 1 byte of data, where the ninth bit is actually a parity bit, which is used for error checking. Um, and then we also mapped the P key to support pausing the program, and as I said, anything over a byte is invalid as input. To discuss I2C's communication and how it works, we first say that for using the logic, when always with FF being a flip-flop, and every rising positive edge of the clock, meaning a key pressed, this operator is used as a non-blocking assignment to mimic how a flip-flop would be transferring data. And this is important because in these ways of serial communication, either they're synchronous or asynchronous. However, it's important to note that these are fundamentally made to interchange data, and we should be mimicking this in the most efficient way possible. The two parts of I2C which mitigate syncing the two serial lines and actually addressing all of the bits passing through them. SDA is the data line acceptance port, which is doing the addressing of data. And then SCL is just the clock line, which is syncing the two serial lines. And that makes it synchronous as opposed to UART, which is asynchronous. To get into the actual code, first, this I2C one's very well commented, so maybe I won't spend as much time on it as I could UART. However, I will note that this ACK, this is a sort of, this is the ninth. You'll see that we have this 1 byte of input, and the ACK is sort of parity bit where we're performing error checking. However, this error checking is not as good as you'll see in UART, as you'll see in a second. And then in terms of some changes, we used logic here instead of, we found that using like wire or reg, in some cases it's better, it's synthesizable, but this is a little bit faster to do it this way. These two tri-states are the SCL and SDA lines, which I previously discussed, their function. And as we pass through the very beginning of the program, a buffer, the SDA and SCL lines are fed through this buffer because of the way master-slave hierarchy works in I2C. So this master module is initiating the bus transfer of data, where this actually is generating the clock to open the target device, which is the keyboard, and address it such that we can synchronously pair the two. That's what this SCL line is doing here, regardless of what this value is, this 1 bit. And this is actually addressing it, so performing the SDA serial data line operation. To go further through all of these states, I feel would be trivial. So let me explain my UART. With UART, the way this communication functions, it actually eliminates entirely the need for a clock, because we have this arbitrary rate, the baud rate, where it's not quite arbitrary. I mean, it's to see the bits per second transfer rate through our program. In some way, that's arbitrary, but it's also important to note that this eliminates the need for a clock. So in this generation, the exact way where the baud, 16 in this case, is functioning with the FIFO and the UART is that, well, allow me to go through the state table, and this should be pretty clear. So this is the initial buffer that this flip-flop will pass through. And then to get to the actual state table, so the UART is considered idle at the point where the input is low after the start bit has been acknowledged. So this first part is to acknowledge the start bit and such, and then receiving basically starts a counter, and this counter is in the 8th cycle of baud 16 at this time. And then as this is being checked, this state, so if receiving is still low during the 8th cycle of baud 16, we'll see that that means we have the wrong start bit. And UART is going to be better by the fact that this start bit, this parity bit, all this stuff, it's error checking. And this may cause a lot of interrupts in our program. So the last thing I'll acknowledge is when these actually occur. When the start bit is valid, in this case, the data is sampled every 16th cycle of baud 16. And when receiving is then high, the stop bit is acknowledged, and we can finally stop the sending of data from the UART. And the UART is also great in efficiency because it will only continue sending data as there is still data in it. And that makes a little more sense with what the FIFO is doing, where we see that the frequency of how much the UART is going to be interrupted by its error checking and the CPU's inefficiency, the FIFO and this other module, the FIFO controller, this function wrapper, allows us to boost the transmission and receiving efficiency. And our data frame in this case is of the size 8, where I said that we have a byte of input. And yeah, that's why we use the FIFO with the UART to bring it finally full circle. These LED mux and LED mux core, LED mux 2, this is a wrapper around LED mux core where I addressed all of the LED in the LED array such that once you have a greater input in the keyboard, so if it's 111 instead of 000, it's going to flash the lights for a longer time sequence than if you did a smaller number input. And yes, those are all the great functions of our code.